Welcome to Electronics Pariksha channel. Today we'll discuss some more problems of diode circuits from analog electronics. We'll see the first question. A PN junction is in series with the 100 ohm resistor is forward biased so that the current of 100 milliamps flows. If the voltage across the combination is instantaneously reversed to 10 volts at time t is equals to 0, the reverse current that flows through the junction at t is equals to 0 is approximately given by. So, when the diode is forward biased, if you see the functioning of a diode, when the diode is forward biased, this is the p type and this is the n type. See, p type is connected to positive plate and n type is connected to negative plate. When it is connected like this, whatever the holes in the p type, they will be crossing the junction. So they will be pushed towards the junction by this positive plate. Similarly, the negative plate pushes the electrons in the n type towards this junction. So there will be huge accumulation of the charges across the junction. And these charge carriers recombine. These charge carriers recombine and there will be huge current flow. Electrons move in this direction, holes move in the positive direction. Holes move in this particular direction. So we accept the conventional flow of current in the movement of hole. So the current flows in this direction, whereas electrons move in the reverse direction. So now what he is telling in this scenario, when you reverse the voltage, he is telling when you reverse the voltage means here you have to reverse the voltage means the positive plate is connected to positive p type is connected to negative plate and n type is connected to positive plate. When you reverse the voltage like this, what happens to the current flow? See, when the voltage v across the diode is reversed, the current flowing through the current I flowing through it will not stop suddenly. Will not stop suddenly. Why? Because there is already a huge accumulation of charge carriers in this zone. In this particular zone, there is a huge accumulation of charge carriers. These charge carriers need to understand that the voltage appeared here is reversed. So it will take some time. That is called reverse recovery time. It is called the reverse recovery time. The reverse recovery time is the time taken by the diode to switch from forward conduction state, forward conduction state to reverse blocking state. Okay, that is the time taken by the diode to switch from forward conducting state to reverse blocking state. Till that time, the diode usually allows the same current to flow. Hope you understood this point. Now, if you see the graph will be like this. There will be diode is conducting in a forward mode. Okay, this is the forward voltage. Diode is conducting in a forward mode. This is the forward current IF. When the voltage has changed its direction, means reverse voltage is applied immediately. The same current now 100 milliamps is flowing in the forward conduction state. The same current flows, but the direction changes. This is minus 100 milliamps. Actually, the current direction does not change here. This is very, very important. The current direction doesn't change. What has changed? The voltage direction has changed. So when the voltage direction is changed, current is flowing in the same way. So current is opposing the applied electromagnetic field. So that's why we are considering this same current as a negative current. But actually what happens? The voltage changes. So same amount of current flows, but as the voltage has changed, we have to consider this current as minus. For how much time it changes? Same amount of current remains for the period TSS, that is the storage time. Storage time is the time taken by the majority charge carriers or the minority time taken by the charge carriers which are accumulated across the junction to understand that voltage applied has got reversed. That is the time taken by the charge carriers to understand. And the voltage applied becomes reverse. Afterwards, once the charge carriers are settled and understood that the voltage is reversed, they will try to move apart. Now here, the positive holes will try to come towards negative plate. Similarly, the negative electrons will try to come to positive plate. They will try to move in the reverse direction, means move away from the junction. So what happens? Gradually, the current flowing through the junction reduces. So it eventually falls back to zero. Ideally zero, but practically it will be nanoamps. Or so the current slowly reduces and becomes zero. This time is called transition time, TTR. Okay, the transition time is the time taken by the diode to switch from maximum current to minimum current. So this two time intervals put together is called reverse recovery time. Is called reverse recovery time. So now at the instant t is equals to 0, this is t is equal to 0. This is t is equal to TSS. This is t is equals to TR. Now at t is equals to 0, what is the current flowing through the diode? That is 100 milliamps. Same 100 milliamps flows through the diode, but in a negative direction. But in the options, it is not given as minus 100 milliamps. It is given only the magnitude. So answer is option D, 100 milliamps. We'll see the next question. In the circle shown below, the diodes are ideal. Good. The value of V0 is. So diodes are ideal. Means there is no cut-in voltage. No cut-in voltage. So if you redraw the circuit, 0.5 volts is applied as input voltage. There is a resistor of 100 ohms. There is a diode D1. And the zero point 0.6 voltage is applied as a bias voltage for this diode. For the diode D2, 0.8 voltage is applied. That is negative 0.8, means minus 0.8 is applied. What is the output voltage? If you observe carefully, let's go step by step. Assume D1 is on and D2 is off. If you assume D1 is on, diode D1 should act like a closed switch. There is no voltage drop across the diode D1 because it is ideal diode. Is this really possible? We have to see. If you assume D1 is on and D2 is off, D2 is off means open switch. But is this really possible? It is not possible because if you see D1 diode, P type is connected to 0.5 volts, N type is connected to 0.6 volts. For a diode to conduct, P type should be connected to higher potential, N type should be connected to lower potential. But here in this case, in this case of D1, P type is connected to 0.5 volts, N type is connected to 0.6 volts. So this is not possible. So the diode D1 cannot be on. So let us assume diode D1 is off, that is open switch, and D2 is on. But is this possible? Is this case possible? It is also not possible because D2 P type is connected to minus 0.8, whereas N type is connected to plus 0.5. Again, here the case fails. P type is connected to lower potential, N type is connected to higher potential. Even D2 is reverse biased. So even D2 remains open. So in this case, we have to write here D1 on and D2 is off. This is not possible because D1 is reverse biased. Similarly, D1 off and D1 on condition, D2 on condition. This is also not possible because D2 is also reverse biased. So what we have to consider, both diodes D1 and D2 both are off condition. Both are in off condition. This is correct. Then what happens to output voltage? Output voltage is similar to input voltage, that is 0.5 volts. So answer is option B. Here one more thing is D1 and D2 both cannot be on. Both cannot be on state. Why? Because D1 and D2 are ideal diodes. If both are on, if both are on, what happens is this is zero point 0.5 volts. D1 acts like a closed switch. Here it is plus zero point 0.6 volt. And D2 also acts like a closed switch. And here it is zero point 0.8 volts. That is minus zero point 0.8 volts. So here D1 and D2 both are ideal diodes. For the parallel branches, voltages must be same. If you apply Kirchhoff voltage law in this loop, that fails. So KVL in this loop fails. This is not possible. For the parallel branches, always the voltage must be constant. You must have studied in network theory because parallel branches must have same voltages. Branches must have same voltages. But here it is different. This is zero point 0.6 volts and here it is zero point 0.8 volts. So this is not possible. So answer is option B, zero point 0.5 volts. D1 and D2 both diodes are off. Now we'll see the next question. When the input waveform and circuit of the clamper is given, is shown in the figure, and a DC voltmeter indicating the voltage across the output A and B are. Here, if you observe the circuit, this is not clamper, this is a voltage doubler. A voltage doubler. In voltage doubler, we have two types. One is half wave voltage doubler, and the next one is full wave voltage doubler. So what is half wave and what is full wave? Simple sense, if you are taking the output across single capacitor, then it is half wave voltage doubler. If you are taking output across two capacitors, if output is across two capacitors, then it is full wave. Two capacitors. If output is across one capacitor, then it is half wave. That is simple way to understand. Now we'll see the circuit's operation. This is the input voltage and this is the capacitor C, and this is the diode D1, this is the diode D2, and this is the capacitor C2. This is C1 and this is C2, and output voltage is taken across C2. So what is basically a voltage doubler? Voltage doubler is converts input AC voltage into output DC voltage whose amplitude is two times of input voltage peak value, that is 2 Vm, 2 times of the maximum input voltage. This is the basic operation of voltage doubler. Now how does this happen? We'll see. See, input voltage is sinusoidal waveform. During the positive half cycle, the diode D1 conducts and the current flows through C1. So during this period, there will be a voltage across C1, that is plus Vm. The voltage across C1 is plus Vm. Vm voltage will be there. Okay, this is during the positive half cycle. During the negative half cycle, what happens? If you redraw the circuit, during the negative half cycle, the input voltage will be like this, minus and plus, and there will be the voltage across capacitor C1, that is plus Vm. Here it will be like this. This is the voltage across the capacitor. Diode D1 does not conduct because it is reverse biased. Diode D2 conducts. So now the capacitor allows the flow of current. If you see in this case, during the negative half cycle, the current flows in this direction through the capacitor C2 and diode D2. Okay. So in this process, the capacitor C2 is charged to the voltage of 2 times of Vm. Why? Because there is a voltage of V minus Vm. There is a voltage of minus Vm at the input voltage, and also see here there is a voltage of Vm and the input voltage and Vm voltage across the C1. Both voltages appear across C2. So it will be charged to 2 times of Vm. So the output voltage here is minus 2 Vm. Okay. So what is the Vm here? It is 10 volts. It is given in the diagram. So the output voltage V naught is equals to minus 2 Vm, whereas Vm is equals to 10 volts. So total output voltage is minus 20 volts. This is the function of voltage doubler. So answer is option D. Now here comes 2 questions are there. The circuit in the figure is best described as. See, if you observe the circuit carefully, this is nothing but a voltage doubler. This is nothing but a voltage doubler, but this is a full wave voltage doubler. This is nothing but a full wave voltage doubler. I will redraw the circuit. This is the input voltage Vin. This is the diode D1 and capacitor C1. This is the diode D2 and capacitor C2. Here output is taken across 2 capacitors. So it is a full wave voltage doubler. Okay. So here the same principle applies. What happens if you see, observe during the positive half cycle, diode D2 conducts, current flows through C2. Okay. This is during the positive half cycle. Capacitor C2 charges 2 voltage plus Vm. Similarly, during the negative half cycle, the current flows through the diode D1 and C1. So this is during negative half cycle. Okay. So capacitor charges to Vm in the reverse direction. So the output voltage, if you see, it is nothing but Vm plus Vm, that is 2 Vm. Output voltage is nothing but Vm plus Vm, that is 2 times of Vm. So this is simple voltage doubler, and this is the full wave voltage doubler. So now we'll see the basic differences between a full wave voltage doubler and a half wave voltage doubler. Full wave voltage doubler and half wave voltage doubler. In a full wave voltage doubler, the voltage is taken across 2 capacitors. Output is taken at 2 capacitors. Whereas in case of half wave voltage doubler, output is taken at single capacitor. Second thing is, in a full wave voltage doubler, the regulation is high. Regulation is high and ripple content is low. Whereas here, regulation is poor in a half wave voltage doubler. Third difference is the maximum voltage across capacitor is in full wave voltage doubler is Vmax. Whereas in half wave voltage doubler, it is 2 times of Vmax. This is true. Even here, if you see, the voltage across C2 is plus Vm. Voltage across C1 is plus Vm. So that is the maximum voltage across a capacitor in full wave voltage doubler. Whereas in case of half wave voltage doubler, here this is half wave voltage doubler. The voltage across C2 is 2 Vm. That is the maximum voltage across a capacitor, 2 Vm. Okay. Now here, the fourth common thing is there are 2 diodes and 2 capacitors in full wave voltage doubler. In half wave voltage doubler also there are 2 diodes and 2 capacitors. Okay. Now let's see another question. Here they have given one more question. The components of a full wave voltage doubler. It's 2 diodes and 2 capacitors. Option C.
Sri Raghava Academy online coaching center for the regular and backlog students dedicated to diploma and engineering courses. Semester wise and subject wise coaching is available. Contact the number 70192 46753.